Okay, let's continue. Alright, this is going to be part 8. We continue our introduction for thermodynamics or thermochemistry, either way you name it. Now we talk about a closed system. What is closed system defined? As a system only allows energy to be exchanged between the system and its surroundings, not mass, so that we are able to eliminate one of the two variables and we concentrate on the study of the energy involved in the process related to the system we are interested in, right? So because of this we are able to handle it. So it is a system we are able to study with one variables, that's the energy, alright, energy. Now, if we talk about energy, we already talked about two processes involve the exchange of energy, right? Seems like you heat up the water from the bottom of a pot and the thermal energy, the heat, right? Or it's called infrared radiation, right? Get into the pot, absorbed by water, water starts to raise the temperature as a sensible heat, goes up to 100 degrees Celsius at the boiling point, and then they still continue to absorb more energy and then lose up the intermolecular bonding between the molecule of waters, and then the water separated from the liquid and go into the space as individual gas molecules we call steam, right? So the energy was absorbed. That is endothermic process. The contrary, the backwards, if the steam gets cooled down, will give away the heat, right? And will be condensed back to liquid water. So that heat will be given off from the water to the space, right? Or infrared, or the heat, or thermal energy, whatever you call it, they are the same thing. And then the water recondensed back to liquid water. Now, the energy will be given off to the space. To the water, as far as water is concerned, the water loses heat to be condensed. The steam loses heat, getting condensed back to water, and the water absorbs heat, getting boiled into steam, right? So you have the direction of the energy being absorbed and the physical state changes. So we talk about two. In the past, we talked about two. One is what? Endothermic, right? Absorb heat. Absorbs heat, right? Right. And then the number two is exothermic process, right? Released or give off the heat, right? Now, absorb heat by who? By the system, right? Or surroundings. Now, it depends on what you study, right? How do you define, right? And what is the direction of the heat? Heat flow, right? And here, release heat. Release heat. From who? Right? From who? From either the system or to the surrounding, right? Or vice versa, from the surroundings back into the system, right? That's the two situations about a thermal process. There's one more we haven't got time to talk about. The third kind, right? You got endothermic, you got exothermic. Both involve exchange of heat or exchange of thermal energy between the system and its surroundings, right? Is there any way there's no exchange? Of course, yes. So what do we call that? What kind of process we name it? We call isothermic. Right? What isothermic means, there's no exchange of energy between the system and its surroundings. Not at all. No exchange of energy, right, between the system and its surroundings. Now that is also possible. So we list all these three possible processes involving energy exchange, right? Either it change this way or opposite or not at all. Right? We list all of them, right? We list all of them. Now, then when we talk about energy, right? Before we get into the spectrum of different type of energy, right? At least we are going to talk about the electromagnetic radiation from the sun, the solar ray, and the spectrum. Its spectrum. We're going to get into something we are going to discuss first before we get into why different radiation will have different amount of energy, right? And strong or weak or high energy or low energy. Now, what are those we are going to discuss? The physical properties, right, related to the strengths of energy. Right, let's talk about this. So here is the physical properties related to the strengths of different type of energies, right? We are going to concentrate on the two properties. The first one, we're going to introduce the frequency of the radiation or the energy. Frequency of the radiation, right? The energy, right? Now, the fact is, the higher the frequency of the radiation, all kind of radiation we talk about here is it carries the energy around, right? So, the higher the frequency, the highest energy of the type of radiation possess. So, the frequency has a symbol we use as mu. It's pronounced mu. And they look like a V, but it's not V. Okay, it's a little difference there between. And then the frequency is, let's say, all right, it's frequency, right? Frequency. And the energy, right? Energy we use E is directly proportional to the value of the frequency. So the higher the frequency, all right, and then higher the energy it possesses. All right, and what is frequency? We talked about this just a little bit. And then the second one is the wavelengths. Wavelengths of the radiation. All right, and of course, this different kind of energy will have different kind of wavelengths, right, based on different kind. And what is wavelengths? The symbol we use, I think it's Greek, and then it's called lambda. Look like this, lambda. Lambda. And the wavelengths is inversely proportional to the amount of energy any type of radiation possesses. So the energy level is inversely, the fish goes the other way, that's a fish going to the left, that's a fish to the right. Oh, if you don't know that, that's a symbol for directly proportional or inversely proportional to the lambda of frequency. So the longer wavelengths, right? Wavelengths is the lengths, right? The longer the wavelengths, right? The lower the energy and the radiation possess. All right. So these are the two properties we're going to talk about, and then we're going to list the different type of radiation involved in the solar array we call electromagnetic radiation. Then we are able to understand how those radiation plays out their role in all kind of routine life-related device. All right. So first, how do we understand the direct proportional relationship between the frequency and the amount of energy the radiation possesses? Right. Let's say if you are able to play sports, say basketball, so you must have dribbling the ball in your life, right? So if you have a basketball, you start to play it, pat it on the ground, right? And you want the ball to be up and down faster. What are you going to do? Fast means, the frequency means how many times this kind of action will repeat in a unit time frame. How many times, how many up and down will happen in 1 second. That's called the frequency. In physical science, we don't want to get the units. We get into a general conceptual definitions. So if you pat the ball, dribbling ball, you want the ball to dribble up and down faster. In other words, it will up and down more cycle in shorter time, or more cycle in per seconds. What do you have to do? You have to keep on patting the ball. When the ball jump up to your hand and you push down again, synchronize at the frequency, and then the ball will be keep on constructive, right? Constructing, dribbling up and down in short period of time. So think about it, patting the ball continuously. What do you have been doing the patting? But you keep on adding more energy, am I right? So you're adding more energy into the ball, the basketball. The basketball will gain the energy from your hand to be able to jump up and down much faster. So the frequency of a ball, right, dribbling ball up and down, is directly related to the energy amount you input into the ball. So that explains the energy level of any kind of radiation is directly to the frequency of the radiation it possesses, right? That's number one solved. Number two, how do we understand the wavelengths? It's inversely proportional to the amount of energy. Now, first we think about this. If you want to penetrate a wooden board, plywood, very thick, half-inch thick. All right, you want to use your thumb. You put all your mighty force to push your thumb into the board. Can your thumb go into the board? Of course not. And but how can you get into the board? Not use your thumb. Use something else with your arm to push the same force to get into the board. Well, you probably think about a knife, right? Not just knife, the tip of the knife, right? And if you use the knife, say the knife looks like this, A knife look like this, right? A knife look like this. Right? A knife look like this. If you want to cut the board into with this edge, of course it's sharp. Right? It won't be able to cut too deep. Use all your force. But if you use the tip going that way into the board, right? The board, the plywood board, you probably can stick into it for ½ inch, or if it's not ½ inch, at least ¼ inch. Why? Because use the edge of the knife, right? Is this long, right? But tip of the knife is so short, so narrow. All the force will be concentrated on the tip, right? So you are able to penetrate into the wood much deeper. So use this concept. Use this concept. For instance, if we are still have the class in classroom, right? If you remember the door, there are 2 doors in the classroom on both sides. It's going to be about 7 foot tall, right? 7 foot tall. Everybody in my class would have no trouble to walk in to the classroom, sit down, listen to my lecture, learn science, with any problem. Because everybody is shorter than door frame, right? Think about the body lengths as the wavelengths. What about the Chinese basketball player Yao Ming? Or think about Shaquille O'Neal. How tall he is? 7 foot? Does he have to bow his head in order to get into the door of the classroom to take my class every day? Of course he has to, because he's slightly about a couple inches taller than the door frame. So if he does not bow his head down, he's going to hit his forehead. Am I right? So use the body, human body lengths to relate to the wavelengths. Now we are able to connect. How do you connect? You say, I still don't get it. Well, that's a knife. You put force on there, it goes in there. We understand that. Now you talk about human body. The human body taller. But it's not, that's not, the human body length is not wavelengths. Oh, it is. It is. It is. It's the same. Why? Because the knife can penetrate into the board deeper, means it has more power, correct? If you have more power in short period of time, that's related to you have more energy. Am I right? We talked about energy, work, energy, and power, didn't we? Right? A couple of parts ago, like a part 4, motion 4, motion 3. So, the power actually relates to the energy, correct? So, if that's the case, the penetration power, right, directly relate to what? Directly relate to, right, the power of energy, right? So, if you are able to penetrate deeper, right, with the same amount of energy, then means you are more powerful, right? So you have more energy to do the same thing without the short wavelengths. But if the wavelength is getting shorter, you are able to penetrate more, so you don't have to put more energy there. That means you are more powerful, or more energy. So if you have a dagger, it's already broken in the end, you probably won't do that as the knife. So what I'm talking about here is the longer the wavelengths, right? Right? The lower the penetration power, which means the lower energy, right? Lower the power, lower the energy, right? So you say, okay, somebody give you a job to do. You say, oh gosh, I'm so tired. I don't have the power, right, to do this job. Because I run out of energy, I'm sick. I can't do the work. It's the same. You talk about that all the time in layman term, right? Every day. So now we understand. If the longer wavelengths cannot penetrate into the board easily, or just like you cannot walk through the door, you have to shorten your body lengths, just like you shorten the wavelengths. So you are able to penetrate more. That means you're getting more power and then relate to more energy. So the shorter the wavelengths, the higher the energy. The longer the wavelengths, the lower the energy. Now we are able to continue because we understand that, right? Now let's introduce the spectrum of different type of radiation in the solar array, which called electromagnetic radiation. Alright, it's quite interesting if we draw a picture and put spectrum into a drawing picture, and then we are able to discuss. Alright. Okay, let's give a title. Alright. What are we going to talk about? We're going to talk about the spectrum of electromagnetic radiation. Now that's the tech term. In layman term, electromagnetic radiation, most of top of solar radiation from the sun. The sun will have exactly the spectrum. Now what does spectrum means? Spectrum means different type of radiation lined up in a sequence with different wavelengths, from the shortest one to the longer one, or vice versa. And then we're going to list them the same way, but also we're going to add more components in there so everybody can follow and understand. We're also going to apply each different type of radiation has been used in our routine life, right? You already have my notes, right? I don't know the page, about 30 page 30 or something. So let's see. Let's draw a line, draw a straight line. I don't care about the straight or not, but just like this, alright? So spectrum spread, right? Like a number line, but it's not a number line anymore. So here, on the very left, I'm going to list it, the radiation stuff from here all the way the spectrum line up to the other end. Alright? So here we're going to say on this left end, we consider it has the highest frequency. In other words, approach to the left, the radiation will have a higher and a higher and a higher frequency, right? What is frequency? Mu, right? Right? And also, since it has the highest frequency, of course, it's directly proportional to the energy, so the energy this side will be higher energy. But also, it's inversely proportional to the wavelengths of different type of radiation, right? So this side will be what? Is the longest wavelengths or shortest wavelengths? Of course, it's going to be shortest. No, shortest wavelengths, lambda, right? Lambda. Alright? And then because the highest frequency and the shortest wavelengths are all represented by the radiation has the highest energy. So you will have highest energy. Right? E. Right? E. Of course, highest energy, you normally will have what? The highest power of penetration, right? So you have a highest penetration power. You may say P, I don't know, right? And then the fourth, number 4, the last line we're gonna put application of, right, of each type, right, each type of radiation. Okay, on the other side, we're going to have the opposite. Here's the highest frequency, here will be lowest frequency. right? Lowest frequency, mu. And shortest wavelengths on this side will be longest wavelengths, right? Then you're going to have lowest energy because it's opposite, right? Energy will be E will be lowest. Lowest energy the radiation on this end possesses, right? And then the penetration power on the left is the highest one, right? The P is going to be, right, lowest or weakest, right? Penetration power. Now application will be separated. We're going to use this bottom space. The very first one on the left, what are we going to put? Now, as we know now, it's called a cosmic ray. Cosmic ray. Cosmic ray has the shortest wavelengths, highest energy, and you go to space without the protection from our atmosphere and our Earth's magnetic field, and your body will be bombarded instantly from the cosmic ray and you'll die instantly. That's why the astronauts all have to wear what? Space suit. Not only keep them warm and with air, they can breathe, can have moisture, can live, but also protect them from the bombardment of cosmic ray to kill them instantly, so they can still go spacewalk. You all know that. Cosmic ray. So that's marked here. Alright, that's the far left end. Then the next one is gamma ray. It is also a very harmful ray because it still have short wavelengths, which is like a sharp knife, just like cosmic a dagger. You can use very small force to peer into anybody's body muscle and kill somebody all the way to the heart, if there's no bone in the middle, right? The gamma ray is very harmful. You probably never heard of these two rays. That's fine, but we learn, right? Then the third one you probably will never forget. You already learned. Also very harmful, very high energy, very short wavelengths, very high frequency, and everybody heard that name, and you probably had an examination with it. It's called X-ray. Now let me explain. If you know X-ray and you've been taking X-ray examination of your fracture of your bone, or you have any possible have a tumor, anything, right? CT scan, X-ray as well. So what happens if you are the patient? The examiner of the machine operator told you to hold your breath, right? Hold your breath. And they say, okay, hold your breath for a few seconds. They say, hold your breath, and you get psss, very small sound for a couple of seconds. But where is the operator? They back off quickly into the booth. The booth has a window, but that window is not regular glass window. It's the glass doped with some heavy metal, lead particles, lead atoms in there. So the heavy metal is able to stop the X-ray penetrating through the window to expose the operator and the X-ray constantly every day, shift 8 hour a day. They're going to kill it in no time because X-ray concentrated, going to kill people, and the people under X-ray for long exposure and X-ray will get cancer in the blood. We call leukemia. Right? So that's why even in the old time, your relative will be given a jacket. Put on your body, protect your chest in front, and you can stay with your parents and hold them and help them. And the operator go back, the operating machine goes on, and the X-ray going to your mother or father, and you were protected because you have a lead plate inside the jacket, protect X-ray to get you from the X-ray. So that's how you are under a protection because X-ray is harmful. Now time's up. Okay, let's stop here and then continue to finish that next section. All right. I don't know what it is.
Oh,